Hi everyone, welcome back to Chem Help ASAP. In this video, we are going to identify polar and nonpolar molecules. Let's get started.
Let's start by distinguishing the difference between a polar bond and a nonpolar bond. So a polar bond is created when two atoms with different electronegativity values form a bond. A nonpolar bond is created when two atoms with the same electronegativity values form a bond. Electronegativity is the ability of an atom to attract an electron. So this periodic table here shows the value of electronegativity for the elements. Fluorine in the upper right has the highest electronegativity value, so it attracts electrons very strongly, as opposed to cesium in the lower left, which has a very low electronegativity, which makes sense. Cesium wants to donate an electron, not gain an electron. Let's look at some molecules and the bonds they form. We're going to keep our periodic table up with our values of electronegativity. Let's first look at the bond between nitrogen and oxygen. So nitrogen has an electronegativity of 3, and oxygen has an electronegativity of 3.5. That is a difference of 0.5 between nitrogen and oxygen. Therefore, when they form a bond, oxygen is going to pull the electrons more strongly towards itself. This polarizes the bond. The electrons spend more time around the oxygen than they do around the nitrogen. The way we note this is a lowercase delta, which symbolizes a partial positive or negative charge. So for the bond between nitrogen and oxygen, we are going to note a partial positive charge by nitrogen and a partial negative charge by oxygen. These are not full formal charges, like you might see on the sodium cation or the chlorine anion. These are full formal charges, not partial charges. Nitrogen and oxygen do not share their electrons equally, but they do still share their electrons. We also specify this unequal sharing with an arrow. For the nitrogen and oxygen bond, it looks like this. You can see the positive end is at the nitrogen and the negative end is at the oxygen. It points towards the oxygen. We call this arrow the dipole moment. And again, it shows that the electrons are shared unequally between these two atoms. Not all bonds are polar. Some bonds are nonpolar. They do share equally. So let's look at the bond between two oxygen atoms here. Because they are the same atom, they have the same electronegativity. Therefore, they will share the electrons equally. So we do not write any partial charges, and there is no arrow because there is no dipole moment with this molecule. Our oxygen-oxygen molecule is a nonpolar molecule, and our nitrogen-oxygen is a polar molecule. Determining polarity between two atoms is fairly straightforward, but sometimes we have multiple atoms bonded. Let's take a look at those. This table summarizes the molecular geometry and the polarity. I do want to caution you, this table is a simplification. We assume that all of these molecules have symmetry. In other words, we assume that the white atoms are the same, while the central atom may be different. So let's take a look at some examples. An example of a linear molecule is carbon dioxide. So carbon dioxide is an oxygen bonded to a carbon, bonded to another oxygen, and it is bonded at a 180-degree angle. It is linear. While each carbon-oxygen bond is a polar bond, because they are 180 degrees apart from each other, the polarities add out, therefore giving a nonpolar molecule. An example of a bent molecule is water. So water is an oxygen bonded to two hydrogens, but the bond angle for water is about 105 degrees. The oxygen-hydrogen bond here for both of these is polar. However, because they're at 105 degrees, they do not add out like the linear molecule. Therefore, bent molecules are polar. An example of a trigonal planar molecule is boron tetrafluoride. That is a boron bonded to 3 fluorines. The bond angle here is 120 degrees. If you remember back to your geometry, this is an equilateral triangle. Therefore, even though these boron-fluorine bonds are polar, just like in the linear molecule, they add out. This is what makes trigonal planar a nonpolar molecule. An example of a trigonal pyramidal is ammonia. So ammonia is a nitrogen atom bonded to 3 hydrogen atoms. In ammonia, the bond angle is 107 degrees. This means the polar bonds between the nitrogen and the hydrogens do not add out like the trigonal planar molecule. Therefore, trigonal pyramidal is polar. Our last shape is tetrahedral. An example of a tetrahedral molecule is methane. Methane is carbon bonded to 4 hydrogens. The bond angle is about 109 degrees. This one is a little more difficult to see, but even though these carbon-hydrogen bonds are polar, they are situated in a way in 3D space such that they all add out. Therefore, tetrahedral molecules are nonpolar. I do want to reiterate again that this table is a simplification. We only dealt with molecules that were symmetrical. However, it is still helpful to determine if a molecule is polar or nonpolar. One of the main advantages of determining if a molecule is polar or nonpolar is because of the rule like dissolves like. What this means is that nonpolar molecules dissolve in other nonpolar molecules. This is why butter dissolves easily in oil, but oil will not mix with water. On the other hand, polar molecules dissolve well in other polar molecules. So water and ammonia do a great job of dissolving. So if you are trying to make a solution, it is important to know your polarities, because if you are trying to dissolve a nonpolar solute in a polar solvent, it simply will not dissolve. You can remember this the next time you see someone trying to dissolve oil in water.
While we used a very simplified model in this video, if you want to know more, I do have a playlist where I go into Lewis structures. I will put that link in the description down below. Thanks so much for watching.